The title of this presentation is very snappy, Prior Formulation and Bayesian Analysis of Biomechanical Data. So this was joint work with two other people at the lab, Connor Piles and Alex Ivaskev. So I guess we'll begin by talking about the setup here, or our problem statement. So the setting that we're in for all the simulations that we're going to be discussing is the setting of an experiment trying to relate a continuous input to a binary outcome. So you have something that you're doing and you want to see if it causes a particular effect. So examples of this in biomechanics and in other fields might come from, example, trying to figure out what dose of a drug you need to get in order to cause lethality or some kind of injury to a patient, how much velocity causes the occupants of a car to die during a car accident, or relating the velocity of a projectile to an injury of a person who is struck by it. So that's our experimental setup here. And one of the common analytic artifacts that you produce from such an experiment is called an injury risk curve, or an IRC. You see a picture of just a toy IRC there. The point of an IRC is to let you look across every value of the input and figure out for that value of input what the probability of observing the outcome is. So the way to read this red point on the notional curve we have here is that when the input is 62.6, the probability of observing your outcome, whatever it may be, is 75%. One other common feature of studies like this is censoring. So for example, you don't have an exact data point. You can't say, well, when my input was 62.6, I did not observe the outcome. And so my data point should be 62.6 comma 1. Instead, you say, well, when my input was 62.6, I didn't observe the outcome. So I know that the input at which I would have observed it is somewhere to the right of 62.6. So you replace an exact data point with something that is like a half interval. And that's also very common in these types of studies. So that's going to be one feature of our simulated data. So let's go away. Okay. So that's our problem statement. The typical way to conduct an experiment to fit an injury risk curve is to just run as many iterations of the experiment as you can. So apply the input, see if you observe the output or not, and then use maximum likelihood estimation to fit a curve to the resulting data set using something like logistic regression, or perhaps you can use survival analysis with a whole family of different kinds of distributions, Weibels, etc. This works well when, of course, you can run as many experiments as you need to. But one of the limitations, particularly in the biomechanical world, is that you can't always run as many experiments as you would like to get a good estimate. Why can't you do that? Well, sometimes experiments are just very expensive to run. The setup might cost a lot of money or time or manpower. If the testing is destructive, so the object that you're testing is wrecked in the process of performing one run of the experiment, then of course that means that you're going to be wrecking a lot of objects, and you may not have as many available to destroy as you would need to get good estimates. Sometimes it's hard to procure specimens. So if you're doing, testing on some sort of live subject or post-mortem human subject, those kinds of things can be hard to obtain. So in particularly the biomechanical world, you're often faced with trying to run an experiment to produce an injury risk curve without the ability to run more than maybe 10 or so iterations of the experiment. But you still want to get a good IRC out of your experiment, and you still want it to have fairly narrow confidence bounds, so you can make fairly confident, correct statements about the relation of your continuous input to your discrete output. So how do you square that circle? Well, one approach would be to use Bayesian survival analysis. So Bayesian techniques would let us use prior information to help to fit an injury risk curve to even a very small data set. And it can kind of stand in for the missing data. Where do you get this prior information? Well, it can come from all kinds of places. And I think some of the other presentations have covered that a bit. You can get it from subject matter experts, people who just kind of know what to expect in these settings. You could get it from previous studies or outside data sets that were studying the same question or an adjacent one, or you might get it from a very high fidelity, maybe physical simulation. So this does have the potential to overcome the small data problem in survival analysis through the application of prior information. And the purpose of the simulations that we ran was to determine what would be the best practices for applying Bayesian priors to the production of an injury risk curve, particularly in a biomechanical setting. So things like, how good do the priors need to be for us to get a good fit? What's the relationship between prior information and the necessary sample size? And generally, what would be the best practices for incorporating priors into our biomechanical experiment? The picture on the right here before I move on is just an example of an injury risk curve. This is, I don't know that it's a real one, but it's a notional one. And it shows you some quantiles of interest. You see the confidence bounds there, and then you see on the bottom and top of the chart, the observed or the data points. So green circles would be ones where you did not observe the outcome, and red ones would be examples where you did observe the outcome. Okay. So that's our problem statement. We want to explore the application of priors and Bayesian survival analysis for fitting an injury risk curve in a setting potentially with pretty small data. So to start with, we had to define what we called a reference curve or the right answer. So of course, in nature, you're not going to have this, right? If you're actually doing a real experiment, nobody's going to walk up and tell you what the exact right curve is. But in this case, because we chose to use synthetic data, we had the advantage of being able to define one from the beginning. So we began by saying this is going to be the right answer that all of our simulated data and priors is going to attempt to recover. We started by defining the quantiles of interest, which we called Q10 and Q90. So Q10 would be the point on the injury risk curve where at that input, your risk of observing the outcome is 10%. Q90 would be the point on the injury risk curve where your chances of observing that outcome are 90%. So we went ahead and set those equal to 25 and 75 just by fiat. From there, we computed the shape and scale of a Weibull distribution, which is a very common type of parametric distribution found in survival analysis, and turned out our reference injury risk curve. So going forward, this is going to be the quote unquote right answer. Once we had our reference curve, we used it to generate some synthetic data. So we generated two data sets, one of 5 points and one of 10. To draw the 5-point data set, we started with the PDF of this Weibull and drew 5 points from it. From there, we used those 5 points to compute the risk of observing the outcome at each one of those input values, and then did a binomial draw using that probability to generate either an observed or not observed result. And from there, we went ahead and introduced the notion of censoring. So anytime we observed the outcome, which here I have labeled injury, we said it was left censored. And when we did not observe the outcome, we called it right censored. You can see our 5-point data set there, as a matter of fact. It is about evenly split between left and right censored points. The same is true for the 10-point data set. So the data is always more or less evenly split between left and right censoring. All right, so from there we have our reference curve and our synthetic data, but then we need the priors that we're hoping to explore. So that's what this next slide covers. We started out by dividing our priors kind of into two families, which we labeled good, but that's in quotation marks, and bad. So what made, oh, and I should say that all of these priors were taken on the 10th and 90th quantiles of injury. So they're essentially your guess starting out for what the 10th quantile of injury and what the 90th quantile of injury should be. We chose to specify our priors in that manner because that is something that you could easily ask a subject matter expert. You might ask them, say, you know, at what value of the input would you expect to see an injury 10% of the time? And at what value of the output would you expect to see the injury 90% of the time? And then they would answer perhaps in a distributional way, and that's where we get our prior distributions. So the good priors are only called good because they happen to be centered on the quote unquote correct answers, which I'll remind you are 25 and 75. But the do have varying widths. So they come in two flavors, uniform distributions and normal distributions. So a uniform distribution would be, you ask your SME to guess the 10th quantile of injury, and they say, well, I think it's somewhere between 0 and 40, but I don't really have any notion of where in there it is. I can't pick a point in that interval that I think is more reasonable than another point. So that would be a uniform distribution. And then a normal distribution, they would say, well, I think it's between, say, 0 and 50, but I think it's way more likely to be at 25 than at 40. And these are both types of distributions you might get out of SME input. All right, so good distributions or good priors were centered at the correct answer, but we did vary their width. For the uniform distribution, the width went from 50, which is very wide, to 10. For the normal distribution, we didn't vary the width, we varied the standard deviation, but we did set the means to be centered at the correct answers. So that's what made things good or bad in our simulation. For the bad priors, we varied the centering of the uniform distributions. So, they should be centered at 25 and 75, but maybe we centered them at 30. So we shifted them left or right of the correct answers. And sometimes the uniform distribution did include the correct answer, but more often it did not. In every case, though, it was not centered on it. And then finally, we had what we called a bad normal scenario, which is where we just said both Q10 and Q90 are drawn from a normal distribution with a mean of 50 and a median of 50. So that's a very wide, very uninformative prior. It's almost equivalent to not having a prior applied at all. So from there, we had all the priors we wanted to test, our notional data, and our reference curve. So the goal was then to use a simulation, or I guess we used RStan's MCMC sampling to fit injury risk curves to each data set and set of priors. And then we compared the fitted curves to the reference to see what approach got us closer to the right answer. All right, so this is an example of some of the results. We got a set of results like this for each one of the simulations that we ran. This one happens to be for the set of good priors, so centered at 25 and 75, that were nonetheless of width 50. So they were very wide. It was a very wide guess. And this is the one that we fitted to the data set composed of 5 data points. So as you can see, after we ran the simulation, the posterior estimate on Q10 and Q90 did kind of narrow in on the correct answer. We got reasonably good estimates for the Q10, Q90 shape and scale of the Weibull distribution. You can see the fitted value, the reference value, and the differences there. And then you can see a picture of the fitted curve that we got compared to the reference curve. So here the reference curve or correct answer is in purple and the fitted one is in blue. And then those blue, that blue shadow is your credible intervals. So you got an actual curve that was a fairly good guess, but your confidence was pretty low. But we're really interested in these results sort of in aggregate so that we can compare different simulation runs to one another and see what the best approach for fitting priors was. All right, so this is a visualization of every simulation that we ran in this fashion for both data sets, 5 points and 10 points, and then for all types of prior information. So we ran our simulations, we fitted the injury risk curve, and we computed the resulting Weibull shape and scale. And then we compared them or plotted them on this scatter plot so we could look at them compared to the right answer. So this black dot here, I don't know if you can see my pointer, this is the correct answer. So this is where a really good simulation should land us. And as you can see, lots of our simulations did get quite close to us. This star here would be what we got when we used that set of bad normal priors or very wide uninformative normal priors. Again, the guess isn't terrible, but lots of our simulations got closer. And something else to notice that is interesting is you can kind of see trajectories here. So every family of color and shape is a different family of prior distributions. So for example, the red squares here are the ones that we got from fitting a curve to 10 simulated data points where the uniform priors were bad. And you can see those are scattered all over the place. But some of them, particularly the quote unquote good priors, really do form a nice trajectory that kind of narrows in on the correct answer as the width of the priors fell down. So this is a presentation of all of our results, and we'll kind of go through chopping them up in other ways to look at what happened more specifically. We'll just go through this one quickly. This is the same picture, but now instead of plotting shape and scale for each of the fitted curves, we're plotting the quantiles of interest, so Q10 and Q90. This looks pretty much like the other picture, just shifted, which is to be expected because shape and scale are computed from a continuous function of Q10 and Q90. All right, so this is a visualization of the subset of data. You could actually probably see a lot of this information in the previous slide that I showed you, but here it's laid out a little bit more simply. So firstly, we've specialized to the case of 5 data points, so the 5 simulated data points that we grabbed from our reference distribution. And we've also further specialized to the uniform priors that were good. So they were all centered on the correct answers for Q10 and Q90. And the only difference is that some were wider than others. So remember that they had widths ranging from 50 to 10. And this shows us pretty much what you would expect. So for every fitted curve, we computed Q10, Q90, shape and scale, and then took the difference between the fitted quantiles or the fitted parameters and the correct parameters and plotted them here versus the width of the prior distribution. And this, as I said, is essentially what you'd expect. So if you follow this first chart here in the upper left-hand corner, what it's showing us is that as the prior distribution got narrower, we got closer to the correct quantile of injury. And it's kind of linear, not perfectly. We see a similar trend in the 90th quantile of injury. So as the prior distribution got narrower, as our SME guesses at what Q90 was got more and more narrow, our guess at the correct answer, or our guess at the 90th quantile of injury got better and better. Shape and scale, because you are transforming Q10 and Q90, don't have quite the same shape. And one thing that's interesting to note here is that though in general, narrower priors gave you a better guess, the effect seems to level out or to flatten out somewhere between 10 and 30. So you want your priors to be as specific as possible, but there is a point of diminishing returns. And here is another way of looking at that same data set that we just glanced, where we have actually pictured the fitted injury risk curves for each one of those sets of good uniform priors against the reference curve to see kind of how close we got. So here the red curve is the reference curve, and you can't even see them, but the other IRCs that we fitted are also here. And they're very, very close to the reference curve. The real difference though is in the width of the confidence bounds that you get. So your guess is very good even with quite wide priors. However, your confidence is very low. And we've made some attempt to quantify that relationship here by plotting the width of the prior at Q10 and Q90 against the width of the confidence bound at Q10 and Q90. And the relationship is quite linear. So you could phrase it in this way. You could say that for every 1% reduction in the width of the prior on Q10, you reduce the width of the confidence interval around the Q10 estimate by about 0.81%. So you basically got about 80 cents on the dollar for trying to reduce or narrow your guess at Q10. And then for Q90, it was about 74 cents on the dollar. So we see here, having priors centered at the right place is really good, but the real power lies in trying to get them narrow enough so that you are confident in the estimates you make at the end of the day. All right. So here is the same picture, but now we have gone to the quote unquote bad priors. So these are the ones that we obtained by taking the correct guess for Q10 and Q90 and shifting it either to the right or to the left by a specified number of units. So the first 4 colors here, we got by just taking Q10 and Q90 and shifting them both either, right by 5 units, left by 5 units, right by 15 units, and left by 15 units. And I guess the thing to notice here is that you get essentially exactly what you would expect, which is you get a curve that has the right shape, but it is shifted left or right because your initial guess at the priors was shifted left or right. And even though our data was drawn from the reference curve, that wasn't enough to overcome how bad our priors were to begin with. The other two curves that you can see in black and purple, we got by fixing either Q10 or Q90 and then just shifting the other reference quantile. And there you get a curve that is closer by distance, but its shape is not quite right. So, what should we take from here? One of the lessons learned is that bad priors are bad, especially when you add them to small data, because the small data isn't enough to correct for the incorrect guess that you made at the beginning of the day before you ran your simulation. So this chart pretty much advises caution. All right. One of the other things we were hoping to explore in our suite of simulations was how much the size of the data you were using affected the influence of the priors that you were applying. So we had two data sets, remember, 5 points and 10 points. And we were expecting that in all cases, the curves that we fitted on the data set of 10 points would be superior to the curves that we fitted on the data set of 5 points, because it's sort of a truism in statistics that more data is better. Well, in this case, that did not turn out to be true, which was a bit of a surprise for us. So again, here we have specialized to the good uniform priors, the ones that are centered at the correct quantiles of interest, 10 and Q10 and Q90. And what you can see here is that for every fitted aspect of the curve, we actually sort of got the opposite of what we'd expect, where more data seemed to muddy the waters and give us less good of a guess. The best explanation we can come up with for this is that the priors were more or less correct, right? They were exactly correct, centered on the right answers, whereas the data points had some noise introduced because we drew their censoring randomly. So if you had very good priors that you were absolutely confident in and that were the right answer, adding more or less random data to them actually moves your fitted answer away from the right quantiles. However, if we make the same chart, but now specialized to the bad priors, the ones that were not centered on the correct Q10 and Q90, we see sort of the inverse story, where in general, 10 points gave us better results that were closer to the reference curve than 5 points did. So I guess the lesson to take here is that more data can in fact compensate for less certain or for poorer priors. But if your priors were perfect, of course, more data just muddies the waters. Okay. This is sort of the final picture we have to show you the results of our simulations. And this just shows you 3 injury risk curves. Red is the reference curve, the same one we've been using all along that we were trying to recover through our simulation. The blue one would be the curve that we got by fitting a curve or a Weibel to 5 data points with the good uniform priors that nonetheless had a width of 50. So this was equivalent to me saying, I think Q10 is somewhere between 0 and 50, and I think Q90 is somewhere between 50 and 100, and no, I can't be any more specific than that. So though we're calling that a good prior, it's quite a wide guess. And then the yellow here would be what we called our bad normal priors, which were very wide and uninformative, didn't differentiate between Q10 and Q90 at all, and were essentially equivalent to making no guess. And what we want you to take from here is notice how much narrower the confidence bounds on the blue curve are than the ones on the yellow curve. Both blue and yellow are pretty close to red, although blue is closer. But the real difference here is that even making kind of a bad guess, a very wide guess that didn't give you a ton of information, was better than the uninformative priors. So this gives us some notion that there is value in this approach, even if there's also some risk. All right, so these are our sort of conclusions and the way we want to go in the future. So essentially, our takeaway is what we said, that Bayesian survival analysis with good prior distributions did let us get accurate injury risk curves in spite of the small sample sizes. We didn't talk too much about the normal distributions, but essentially they weren't terribly different from the uniform distributions. So it didn't seem that that mattered as much as the sample size, the width of the prior estimate, and the prior estimate's mean. The prior distributions had a huge influence on the shape of the fitted injury risk curves. In general, wider prior distributions gave us wider confidence bounds than our injury risk curves and less accuracy. Although again, even very wide ones were pretty accurate. And another takeaway here is that, of course, when the priors were bad and the data was small, we got incorrect results. Sample size was a bit of a shock to us in that it wasn't the case that more data always gave us better results. In fact, more data in the case of already correct prior distributions on Q10 and Q90 gave us less accurate results. However, the bigger data set did seem to be able to correct for the bad priors that we introduced into our simulation. So that's an argument for using as much data as you can in conjunction with your priors. Future work, of course, we'd like to continue to investigate the effect of the prior distributions on the parameters of the IRC. So we would like to set our priors on the actual shape and scale as opposed to Q10 and Q90. That's the kind of thing you might get, for example, out of a previous paper. We would also like to explore the relationship between bad priors and sample size a little more thoroughly to kind of say, if you're so confident in your priors, what sample size do you need to correct for error? Because now we sort of have some proof that bad priors can be corrected by large data, but we want to quantify that. We started out by using data that was an even mix between left and right censoring. We would like to play with that proportion and see how it affects our final outcome. And finally, we would like to figure out how to combine different types of priors, perhaps via a weighting scheme, to see if we can ameliorate the effect of bad or uncertain prior information even further. But for now, that is it, and I'm ready to take any questions.
Yeah, so there's thanks, Amanda. I had one question really quickly, and then I'll get to a couple from the chat. The 5 and 10 points that you used, how were they selected?
Yeah, so we set our reference Weibull distribution, and I drew the input value from the PDF of that Weibull distribution. So I drew 5 inputs from it, for example. And then from there, I used the CDF of the Weibull distribution to get the probability of injury at each one of those inputs, and did a binomial draw with that as the probability of getting a 1 or a 0.
I meant more the X's, like they were random in this case? Like
yes, but they were drawn from the reference Weibull. So they were random, but we made sure that we got more of them kind of where the center of mass of the Weibull was.
Because another part of this is, as we saw in Victoria's, this kind of adaptive approach. So you were looking at good and bad priors, but if you were to use some sort of sequential design scheme, then the impact of you would almost want to see the impact of those priors on how you would even select those 5 and 10 points.
Yeah, agreed. We did more or less pick them randomly, and then we had them fixed for all the different priors we were exploring. But some kind of sequential approach might get you even more accuracy, definitely.
Okay, so we have the first one is asking, more data leads to more inaccurate results. That sounds counterintuitive. Can you elaborate?
Yes. So what we found is that when the priors were more or less correct, when they were centered at the right quantiles of interest, the results we got from fitting IRCs with the bigger data set were less accurate. It wasn't a huge effect. And we think what happened was that we started with priors that were essentially perfect, right? They were already centered at the right place. And then we introduced data that did have some noise because we did this random draw of the outcome using the reference IRC. And I think that's what we were seeing there. But what we did see is that when the priors were bad, i.e. when they were not centered at the correct Q10 and Q90, we got better results with larger data. So big data can compensate for worse priors. And that's what we're really observing here, is the kind of balance between how good and how accurate your priors are and how many runs of the experiment that you do.
Okay, and I think we maybe have, I don't know if we have one more, but there was one. Have you considered mildly disinformative normals as opposed to a reference normal? Disinformative uniforms are going to create a support issue in the posterior. So I'm a bit more interested in how much things can go wrong with disinformative priors with more flexible support.
Yeah, I agree. And that's something we want to kind of explore in our future work, I think, is different families of priors. Here it was quite a narrow family that we explored just to kind of understand the problem space.